Good morning. I'm very happy to be here in Vilnius and really pleased to be here in cinema. It's the first time that I have this kind of environment. What I'm going to be talking today about is what is actually the context of artificial intelligence. I think that we use this term way too much. I think that we need to rethink this actually as a way to augment human intelligence. That's my goal today. I will give you as well kind of like the background, what is Teradata and what we do. So as I said, I'm consulting director at Teradata. What we do is we're a software company and we are focused on analytics. Right now we're doing a lot with data science, machine learning, but we are working with the largest enterprises worldwide. This means that we need to be able to put things into production, to be able as well to bring valuable things to the organization. And that is a very big challenge, especially if you think that if you are working with really large organizations that you have several thousand people who are going to be influenced about the things that you are doing. Things are not very easy, so you have a lot of complexity, a lot of things that you need to have under control. So we have discovered around this that putting data science into production is way more than a technical topic. So it is more as well like an organizational topic, how you need to change that. Things as well, culture of the company. If you have, for example, talking as well kind of many enterprises in Europe, especially in Germany, you have enterprises who has been built to never fail. They have really stable processes, but it's as well kind of a problem right now where we need to experiment. We need to be able to fail. I will explain all that. So how we are building systems, intelligent systems that are helping people just to make better decisions, and how we're putting this into production, and how actually we bring value to organizations. So let's define the use case that we're going to be talking about. So fraud is a really big topic right now. Worldwide is a 20 billion problem. And this is increasing every time. Right now with the digitalization, we have many other ways as well to get different cases as well about fraud. We have different other channels, and as well with the development of technology, we have way more intelligent ways how fraudsters are actually approaching fraud. What we're trying to do is to detect all this. Normally as well, fraudsters as well using intelligent systems, and that's the reason as well where this is a very, very hard problem to solve. So in this case, I'm going to talk about like a financial institution. This financial institution had, for example, the classic problem in fraud is that you can have a lot of data if you want. But to predict fraud is always very hard because it does not really happen often. So it happens really, really just several times. So you have a very, very, very difficult class imbalance here, which means as well that you have low detection rates, yeah, and you have a lot of false positives. So you are always going to have things that you cannot really predict, and that's actually a problem. And if you want to define a use case that is going to be interesting to management, you have to generate value. Of course, here we know that high fraud losses, that fraud generates as well lots of losses. For this bank was as well in the million at that level. But on the other side as well, we knew that this high number of false positives meant that you have a group of investigators, and every day they were getting around like 3,000 new transactions, and they have to be taking a look at it manually. Yeah, so they are as well cost, and that's actually something that we wanted to optimize, and we wanted to figure out how we do that. And as I said, the fast-evolving fraud sophistication, fraudsters, they already know what the banks are doing. They know as well what methodologies they are using, what rules that are actually being used, and that's something that makes as well everything a bit harder. So what kind of fraud do we have? Do we have, for example, customer-initiated fraud? So we have, for example, rental scams. We have the what we knew as well, these Nigerian scams, and what as well makes fraud a bit hard is you have as well these kind of love scams. The problem that we have here is that in this kind of scams, the people are kind of embarrassed and they don't talk about it. So we can as well implement a system when we think, okay, we think that this kind of transactions could be fraud, but they don't really say that was fraud, so they think that's okay. So just as well, lots of people, personalities, and all that kind of stuff involved in this. You have as well fake invoicing, so you have different problems as well that you can build as well different kind of use cases here. You have as well the fraud types as well, like the fraudster initiator. That is kind of like criminal groups that are trying to just make money out of it. And something that is happening right now a lot and is very important and increasing as well in different kind of industries is the ID theft. So many people are stealing as well virtual identities and are of course committing crime with it. It's easier. We have malware that is as well happening even more as well in Europe. And there's the kind of challenges that we're trying to approach. Before I start with the model challenges here, this is everything what we know about it. And everything what I was talking about it was not data science, not data engineering at all. That is a purely business problem and a purely problem that you want to lose with subject matter experts. And that is actually something that I think that is the biggest challenge as well, developing successful data projects into production to bring this kind of collaboration together. We got lots of information always when we work with clients, and we try to understand what they want to achieve, and then we start to see what challenges we're going to have. For example, as I said, the class imbalance by fraud is very, very hard. It's 100,000 to 1. That's actually what we were trying to predict, and we were trying to increase false positives and as well the prediction of actual fraud. You have as well, for example, the assigning labels from historic data. As I said, there is as well many people who are not really telling that they were victims of fraud or something like that. You have as well not all features available in real time. In this case, we needed to react as well very fast. So the use case was not just to create a model and put it into production. It needed to happen as well in real time, and we needed to architect that. And something as well is as well a problem is that machine learning normally sees transactions atomically. This means that if you have a transaction and you put variables in it and you have different kind of variables, you can only see that. And fraud is not working in that way. Yeah, I will be explaining how this is working. But there was the opportunity. This was actually when we said the bank had already rule engines. And we said, okay, we can help with that and we can make it better. So that's what we call the first machine learning opportunity. So we said, let's go to machine learning and let's see what they were doing and what we wanted to do. We have on the right side is actually the global payment interface that the bank had. So our approach here was not just to go with a hype and generate a very new system with cool technology, but was instead of that to augment the current infrastructure and make it better, and actually just create as well tools that generate better decisions. So we have, for example, the mobile payment, e-banking, and the business online. This whole data was coming into a central fraud engine, normal rules. A rule, for example, could be you know that you don't allow transactions that may be fraudulent. They cannot be higher than 500 euros or something like that. Yeah, and what was happened is that they were actually going, and this rule engine was deciding if there was fraud or not. And if it was not fraud, then we came to what was explaining. So you come already to you do a verification and you do a manual evaluation. So everything manual, so you had already technology there going on. And we said, okay, technically, we can automate all of that. And we can just do it by ourselves. I actually had as well 2 weeks ago a conversation in a really big telco in Germany. And I was asked, okay, you are talking about this analytic ops. We call analytic ops DevOps for analytics. You are saying that you can automate that. So you can really automate everything. And I said, yes, we can, but I suggest not to do it. And we define actually the process going into an automatization of or automation, of data science, not to do it fully automated yet, because you need many people to be involved, and there's as well many people who actually are doing like for many years one job, and they think that you need to show them how everything is going to change, and you need to bring the people with you into the project. So what we said is we're going to have on the left side from me, you're going to have, for example, an advanced analytics platform. We're going to build that for you, and we're going to generate their models. We want to start with machine learning, very classic regression models, classic gradient boost, or that kind of stuff. And we start to define this infrastructure. So what happened after that, or the plan was that if you were having like some kind of transaction, it was going to the advanced analytics platform. It was happening, the predictions were happening there, coming back to the central fraud engine, because these rules always exist. You are never going to get rid of them. And what was changing is that in this question, that down under the central fraud engine, there were not a lot that they were saying, okay, now you need to check it again. So we wanted to reduce this number. Just to give you an overview, what I'm talking about, this advanced analytics platform fraud. So how we actually explain that, what is actually what we are doing that. As I said, DevOps for analytics is what we call analytic ops. We normally get the data, and we, for example, we have this data science workbench where we actually build the models. You can have your laptop or wherever, but we want to build a process where we can just put it into production. And we want to give the ability of the business to put models into production. So we want to go out from the technical deployment, because we know the data scientists need to see the model and need to actually keep this model, approve this model. But at the end of the day, the business needs to take this decision. So what we are doing for that is, what is the very important part here is, for me, the model validation, model training, model approval, as I said. What we do is you can develop a model or a version of a model, and you can commit this. What is going to happen in this process is that some of your colleagues, what we have a peer review. So everyone is going to have a pop-up, and it's going to say, okay, this algorithm has been changed or is already challenged. It's being challenged. And you are going to have as well kind of like the indicators that are going to help you to decide if you want to approve this model from your peer or not. If you do that, this model is going to be approved, and it's going to be as well, it's going to go to a message to the business owner. The business owner is going to get other kind of information. He already knows what is the result of the model. For example, if I have already my fraud model, and I already know that I have 1,000 transactions per day that I get in average. And if I have a model that tells me I can do better, I can actually just change that. So we are normally building as well kind of like an architecture where we have this challenger champion model architecture, but we don't do it automatically. We could, but we choose not to do it. Just to show you as well a bit, probably a bit more of the technology. So this is not about just one encapsulated technology. So we work with all of that that's available. So as I said, for one bank, we had to use IBM frames. For other banks, we could not use Docker. So we need to adapt actually what is happening and not just use what actually we would like to do. But what we are doing, that's the reason why, the reason as well why we are winning projects, because I want to talk about as well what is a black box here. We already know what a black box is in algorithm terms, but in solution terms as well, very important, because for the people out there that don't understand data science, all of that is a black box. And if you don't give them the opportunity as well to understand the things that you are doing, then you're going to have a very big problem. You're not going to have acceptance to the things that you are doing. So we started this project and we started to show that actually we could be better with this machine learning model. And actually what happened is that we reduce, as you see, for example, here, the false positives rate already in 25 to 30%, and increase actually the real detection of fraud as well in 35%. Of course, here is this is dependent as well how risky the investigators are, because they can, of course, calibrate this. But very important here is that we were trying to optimize this. We already got some traction in this project, and the question was, how can we do that better? That's not better enough. And we thought, okay, there is other ways at that point of time as well. Than this specific case that I have on my mind right now happened, I think, like 2-3 years ago, and deep learning was not kind of like the topic that is right now in Europe. And we thought, okay, we can go into deep learning and we can see the opportunity that we have there. But we have many other challenges to solve that. And what actually we were thinking about at that moment is first one question. Can you build trust based in accuracy? What do you think? Who of you are data scientists here? Can you do that? That was the question that we had. So I thought just a couple of heads saying no. And we said, yeah, that's not possible. We cannot just get better scores and say, okay, we are better, because if I can give you an example, that is a wolf or a husky. Yeah, you can put that in an image recognition. You can put that in a neural network as well to identify that. And if you do this, you can see actually that this algorithm is very good. If you see, all predictions are correct except that one. I think the down right from a side. And you see, for example, that was true is actually a husky, and the prediction set is a wolf. But what happened here, if you're trying to explain that to a people, that's actually very good if you see that it's very accurate. But the problem here is that if you see how this algorithm was making decisions, you see actually that the predictor here for wolf is the snow. So what you were doing here is pretty much building a great snow detector. But you still were very good in doing that. And that's actually the problem that we have right now with many enterprises, depending as well how critical for the society the institutions are. We need to think about this. Because if we're talking about healthcare, if we're talking about human resources, for example, you are going to be building racist algorithms, you're going to be building probably sexist algorithms, you are going to be building some kind of systems that you don't really understand what you are doing, even if you are very good at doing that. And that's actually the nature of deep learning as well. So there are as well some white papers about this, and this is actually something that happens, and I think that the data science community agrees on this. The transparency and the interpretability. When you get more accuracy, you get less interpretability. And this means, for example, if you have a linear relationship between variables, you can just compare and is everything okay. So you have linear regressions or something like that, and that's everything fine. But if you go to non-linear relationships like decision trees or something like that, data scientists still can try to understand what are the key predictors and what is actually driving my model to make decisions. You can actually plot that, and you have many different kind of options to do that. The difference is, but you cannot really do it at local level. And if you have already a multidimensional model like neural networks or something like that, it is actually almost impossible to do that. You could try it, but I don't think that you're going to be successful, especially if the network is very complex. So that is what is getting a black box, and that is what in many enterprises, if we're talking in enterprise level, you cannot go with that. You cannot just say the algorithm told me that. So a key requirement for the black box, for black box models, was the interpretation. So we could not be working on fraud. We could not tell the bank, we're going to work with you, but we're just going to develop an algorithm and you're not going to be able to know what the decision was made. So we were at that time investigating in a project developed by the Washington University, and it's called LIME, and that is actually the local interpretable model diagnostic explanations, which means what this tool, let's call it tool, does is that it goes to a multidimensional model at a local level. So it goes very deep, and it generates as well fake data and tries to map this data as well with original data, and it is already very local and tries to do a linear model out of it, so that can be very easily interpretable. And this way, we could actually build a tool as well for the bank, where we could, for example, tell the people why a transaction was cancelled. A really easy problem about this is just imagine that you want to make a transaction on your bank and your credit card is not working, and you call the bank, and the guy on the line tells you, well, the algorithm tells that you are 90% probable of, a fraudster. So you cannot tell that. You need to explain, for example, why actually this is happening, and you need to be able as well to argument this decision. So that is actually the key part as well of this project, trying to interpret the models and try to understand what these black models are doing. And for that, you need as well an open architecture. And I mean as well from the whole solution, not only from this algorithm. Because something as well that is really important to take away is that many of these big corporations have like really static systems, and this is as well a way and an opportunity to make the enterprise a bit more agile, bringing more service-oriented architectures and all that kind of stuff. So that was a very interesting requirement, and after that we could start talking about like deep learning. We said, okay, let's go to deep learning. We see the opportunity there. What is it? Yeah. We already knew, of course, that the current models could only catch like 70% of all fraud cases. We were trying to tune the models, to do feature engineering, all actually what you can imagine. But there is a point when you don't get better, and you need to do something different. A very as well interesting thing is that traditional machine learning models view transactions atomically. What that means, as I said, you see the transaction and you have the different variables, but you see only this transaction. So what we needed and what we know as well in fraud is that, as I was telling you, if you have, for example, a limit, a really average rule in a bank is that you have a limit of 500 euros or something like that. Yeah. 500 euros in a transaction, then the fraudster already know that. So what they do that, if they want to do fraud, they want to commit this crime, what they do is they do a lot of really small transactions. And the machine learning models, they cannot see that. So we needed to go to an approach that can be a bit more brighter than that. And yeah, exactly, that's what I mean. And often we miss the fraud as a part of a series of actions. And yeah, the capturing of correlation of across many features, I'm going to tell you about that because that's a really interesting feature what we did. So we designed actually to have an architecture of really three common neural networks. So with a conventional convolutional neural network, what we were trying to do is pretty much to really interestingly, we have like really smart people who were really interested already in deep learning at that time, and we were trying from transactions to make a 2D image. So we're trying to make that because, as we know, convolutional neural networks are actually made to detect images and objects and that kind of stuff. So how can you do from a transaction an image? We have as well the LSTM, and what we're trying to do here is to build actually a history of the transactions that we had to catch these patterns that actually from held transactions and we were trying to predict the next one. What is going to be the next one that you're going to be doing, that this user is going to be doing, and if something is going to be changing, we will be able to recognize that. And we had as well the autoencoders, and the autoencoders actually were more like anomaly detection. So we were actually trying to see what is happening that differently. And we decided, okay, we're gonna go with this. To give you, for example, an overview, what we mean as well from making a picture or making a image from a transaction, what we did, and actually that's what our data scientist team did. We had, for example, we built those edges, and these edges were how were they built is that we had like a feature, and we saw the correlation of or in a transaction we see the correlation of a feature that they correlate the most with it. So what we did is actually we put them together, and we put them actually with features that correlate the most. And if you see, for example, the vertical axis is actually kind of like a time axis. So you have like the newest transaction very high and the oldest down, and you have more features, let's say, in the x-axis. So that's the way how we build, for example, the images out of these transactions. And after that, for example, we just do the convolutions as well, going as well with the dimension of times. And if you see, for example, the results that we had here is something that for us, for example, is not very interpretable. It's very much more something that a computer can understand. But if you see in the second the fraud transaction image, you see these red points, and you actually can already detect fraud a bit more. So if you see, for example, inside as well the ResNet model, something as well that for us is not an image, but it's actually for a computer already, we can see some kind of difference. So we could detect fraud out of it. Yeah, so the results that we had here were already very convincing, so we could get a lot of better, and we actually again improved the model in 30%. So at the end of the day, we actually got a lot of better, and from the 3,000 transactions that the guys were actually taking a look every day, we reduced it to 1,000 or something like that, with actually a very big improvement of what actually the business is interested of. We did it, and what were actually the lessons learned here? Actually, I had as well a conversation yesterday, and I was in a round table, and a guy said that we always think about like deep learning just for images over unstructured data, and transactional data can always be solved with normal machine learning models. With it is right, but depends of the case. As you see here, as you've seen here, we had actually transactional data, and we create images off of that. So that's as well creativity. It is as well very interesting that when you are doing data science seriously, your organization is going to care a lot about the quality of the data. So it's going to become a topic. I know that that's always a big topic. And building analytic ops. Was los? Okay, ich bin wieder da. Okay, and building the analytic ops capabilities, for example, that is something that is a blueprint. So we enable the bank to put in production not only one model, but more and faster, because we already built this blueprint. So that is this blueprint approach, just enabling capabilities and not giving just a product that is already done, because the analytical environment is changing a lot currently. And leverage experience, that's as well something that is really important. We had a lot of cross collaborations, multidisciplinary teams, and there was something that was really important as well for the big data team, because we changed, for example, from PowerPoint to production in eight sprints. And really important in that is I always heard about like if you are writing. If you are writing Python, you are doing machine learning. If you are writing PowerPoint, it's artificial intelligence. So kind of like actually bring a bit more context on that. We have as well a team effort that says synergy, inspiration. So there was kind of like as well a start kickoff to do bigger things that the bank is already doing and going through. So through this digitalization process, so it's a very nice opportunity if you actually have the right case. And just to close right now very fast the presentation, so we're already thinking what is after deep learning, but not in this case, just in general. So as I said, I think that the context of artificial intelligence is still in a hype. I think that in the next 1 or 2 years, there's going to be a disillusion because we tend to overestimate the actually we tend to overestimate the short-term capabilities of the technology, and we are doing certainly that with deep learning. I give you an example. You can read these 2 sentences. Yeah, some of you have heard about the problem of common sense in AI. You're very quiet. Okay, that's actually the next problem where normally yet in the US there's lots of investigation around this. And if you read, for example, these 2 sentences, I pounded a nail on the wall. I pounded a nail on the floor. Yeah, very easy. As well for a machine just to read that. But if I ask the machine, yeah, in which case the nail is horizontal, that is something what we call common sense, actually in our normal brain, and we don't need a lot of training data or experience to know that. It's something that we can actually model, we can actually build, we can imagine, and we can actually just say, okay, I know in which case it's happening that. So that's something that deep learning cannot do, and we will see that. As I said, intelligence is just ability to model the world and act on it, and that's not what deep learning is doing, and deep learning cannot do that. To give you, for example, an example, you already know that in deep neural networks, you can actually fool them very easily. You know, we always hear about like, yeah, robots are going to come to us and they are going to attack that. And it happened that at this time, you know, if they just come to us and they try to do, I have a really good news for you, because the only thing that you can do is you go there and you can just wear this pattern and he's going to think probably that you are like a starfish. Yeah, so you can actually do lots of stuff already to fool deep learning. Deep learning is kind of like you have output and you have an input and an output. When you are actually giving the algorithm already the information that you want the algorithm to prepare for you, so you are not giving him the opportunity as well to model the world that you want. So if you change, for example, there's as well this very popular video of Google that they are kind of like showing how a deep learning algorithm is playing very good, you know, and just realizing how he can play very good. Don't remember the name of this game, but I hope that you know what I mean. But there's as well many other experiments that if you just change the environment a bit, for example, if you change the brightness of the ball or something like that, this algorithm needs to learn everything again. And humans are not doing that. If you are playing football and the ball is probably not anymore white, but is right now orange, you don't have to learn how to play football again. So, and that's actually the thing that is a problem. And the next step on deep and actually artificial intelligence is going to be that what we have right now is that you can have virtually unlimited training data. And you have actually very, very little test data, and you think, okay, I can do that. And that's actually a very, very simple way of thinking, because you can just try to put all the experience that you have and you're trying to predict on that. So what is going to happen in the future is that you're going to have that. You're going to build systems that are going to be able to have small training data. So they are going to actually learn how to make assumptions, and you're going to have unlimited. So let's say unlimited human-like test situations. One example of this is CAPTCHAs on the internet. It's the thing that we think as well that make the difference between humans and machines. And very funny is that if you are confronted with that, you can actually understand it and you can actually do it without experience. So you just have common sense and do it. I can probably train an algorithm, and I can train an algorithm to do that. It's going to take a lot of test data to train him, and he's going to learn. But if I decide, the catch-ups are always together. If I decide to change the space between the characters, I'm going to have a problem. So I will need to retrain again and change that. So that's not efficient right now. So talking about that, the common sense problem is the ability to explain cause and effect assumptions about the type and a sense of ordinary situations in an important aspect explainable AI. That's as well why I think that the explanation of AI, the interpretation of the things that we are doing is very important, and as well important to empower the people as well that we are developing for. If we are working on technology, we are pretty much normally as well giving a service. And I believe as well that within the whole artificial intelligence topic, there is, as I said, a lot of overestimation. There's still lots of research to do to get actually where we want to be. And as you see, yeah, that's where we are right now. I think that we are capable right now to bring data science and production. It's something that's going to happen in the next 2-3 years a lot, I think. But yeah, there are these other problems as well where I hope that we're going to have a solution fast and we really can have intelligent systems. And that was everything from me, and thank you very much.